That's that. That's not too bad. Not too bad. Okay, well, let's see. Let's see if there's anybody home here. No, nobody has showed up for class yet. Okay. They'll show up in a minute. I wonder if I need to be further away, maybe an inch or two. Does that help any? I don't know. Not too bad. Okay, what are we going to do today? Well, we're going to do an English auto cycle. Yeah, that sounds pretty good. And a diesel cycle. Okay. Yeah, that'll be good. We'll do an auto cycle. And a diesel cycle. It sounds really good. Let's see if we got any customers. Not yet. Well, it's Monday morning and maybe people haven't awakened yet. Okay. So we're going to do 10.117E. That's the plan. 10, 117, E. Okay. Well, still don't have any. Buddy, we still have 7 minutes, so it's not time for class yet. 10, 117, E. Four-stroke gasoline engine. Compression ratio 10:1. With 4 cylinders of total displacement 75 inches. Why do they tell us that has 4 cylinders? Oh, the total displacement. All right, I think that's for all 4 cylinders. The inlet state. I think I hear some thunder off in the distance. The inlet state is 500 Rankine, 10 PSI, absolute. The engine is running at 2100 RPM. Fuel adding 600 BTUs per pound mass in the combustion process. What's the net work and how much power is produced? Okay, well, great. Well, all right. You know how to do these problems. You write a PV diagram. Yeah. You're supposed to do both. You're supposed to do PV and TS. I think I'm going to be lazy and just do a PV. But I sure wish I had some more customers here. It's 8:25 on my watch. Class starts in 5 minutes. I wonder if there's any interesting announcements. Oh, I graded everybody's test. If you had trouble logging or submitting your test, it's because you waited till after the due date. You can't submit it after the due date because it's not there. You're supposed to submit your stuff before the due date. So we only have one more test, the final exam. And there's only 2 more weeks of school. So when you submit that final exam, do it before the due date. That would be great. Well, we have 4 minutes before class, no big hurry. You guys can still show up. But right now, I don't see anybody. I'm just talking to myself here. Have we talked about the auto cycle at all? I don't remember. I guess I could look at the YouTube video and see what we did last time. No, it looks like we did the refrigeration cycle last time. And then you worked on your exam. And this week, we do the auto and the diesel cycle. Next week, we do the Stirling cycle. We could have a little review. And then your final exam. 2 weeks to go, and we'll be through. So I guess you know nothing about an auto cycle unless you read your book. Well, there's still several minutes. We have, I think, 3 minutes before class. Let me see if anybody's home. Let's see. Nope, nobody's home. Okay. We'll just wait 2 minutes. Even if nobody shows up, I'll go ahead with my lecture because it's on, it'll be posted on YouTube. And maybe that's a mistake. Some of you are sleeping in and just watching it on YouTube. Maybe that's a mistake. But it's not the end of the world. Okay, well, let's start with this auto cycle then. This is 10.117E. And an auto cycle has two adiabats and two isocores. Hey, we have a customer. Stuart's with me. I'm not alone after all. Stuart, unmute and say hi.
Hello.
Hello. How are you today so far?
What was that?
How are you doing today so far?
Pretty good.
That's good. Excellent. Well, we're going to do this 10.117E auto cycle. And it has two adiabats. Well, actually, since it's an ideal auto cycle, those adiabats are reversible. And if you have a reversible adiabat, we have a special name for that. It's called an isentrope. So you have two isentropes and two isocores. So it's going to look like this here. And here, I'll draw it down here. Now, I'm not going to put any vapor dome on this one because it's air. It's like a gasoline engine. It's mostly air with a little gas thrown in there for combustion, but it's mostly air. And so you don't need a vapor dome. You could put some isotherms in there if you wanted. But if you read this, it says the inlet states 500 Rankine, 10 psi. Okay, well here, let me see if I can find some red color here. We'll put a 500 Rankine. Yeah, here we go. Uh, 500 Rankine, here we go. That's your 500 Rankine. See, we're doing this in English. I want you guys to be able to work in English and in SI. SI stands for System International. That's what they used to call the metric system. But here's state one right here. State one. And see, there's an adiabat. Now, adiabats are steeper than isotherms. And so there's state one, goes from 1 to 2. And at state one, you have, we're doing 10.117E, and it says here you have 500 Rankine. Yeah, 500 Rankine. And the pressure is 10 psi. Let me put that over here. We got 10 psi. They have PSIA. That A just means absolute. It's not gauge. It's absolute pressure. Okay, and you go to state 2. And then fuel is added at 600 BTUs per pound mass in the combustion process. Now, you've got 2 iso cores, and going from 2 to 3 goes like this. There's state 3. And then you have another adiabat that comes down here like that to state 4. There's state 4. 1, 2, 3, 4. There you go. 2 isocores and 2 adiabats. Now, what this is the compressive stroke. And you can write that on there if you want to. It's got compression. It's a compression stroke. And see, this is the ignition here. We're going to model that as a heat transfer in. Here we go. We'll have a Q23. There you go, Q23. Heat transfer in during the ignition. And see, here's the power stroke. It gets real hot and then the piston expands and you have the power stroke. And then what happens is you have your exhaust and intake, and we're going to model that as a heat transfer out. There's your Q41. I hear some thunder way off. I wonder if you guys can hear any thunder. Let me see who's with me here. Oh, we have a good class here. We have Stuart, Spencer, Cameron, Bear, and Aubrey. Good to have you guys. I graded all of your exams, and they should be posted on your Blackboard. I even made notes as to if you didn't get 100, if you missed something, I made a note. Do you guys get those notes that I send you? Somebody answer me. Do you?
No, we don't.
Well,
We don't.
what good does it do me to write in there all the information that I found on your test if you never get it?
It showed up for the first 2 homework assignments, but it haven't shown up for anything else. Nothing else has shown up in the grade book at all. The total points is there, so we can keep track of our total score.
But it doesn't tell you what's right or wrong.
Right. It doesn't tell us what our individual grade on any given assignment is.
Okay. Well, look, I'll tell you what I'll do is I'll post the key, and you're going to have to figure it out for yourself. But I will post the key, and then you can compare yours with the key. And if it's not the same as the key, you made a mistake. I guess I don't know what else to do. There's got to be a way. Why would they have me? They gave me a space there for my comments, and I made comments on all you guys. I don't know. I need to talk with one of the higher ups that knows what they're doing on the Blackboard. We'll figure it out, but it ain't going to help you guys much. But I will post the key. Maybe that'll help. Okay, now we're doing a auto cycle now. Thank you for answering that and telling me that. Let me make a note of that so I can remember.
You should have that screenshot I emailed you of the way my Blackboard grade page looks over the weekend.
Is this Stuart?
Spencer.
Spencer, you
Yeah,
emailed
when we
me. Okay, I'll look at that, Spencer.
Yeah, so that way you have something you can show the higher ups and say, this is what my students are seeing.
Thank you, Spencer. I will look at that. Okay, I made a note. We'll do the best we can on this. Thank you for suffering with me on this stuff. I'm learning just like you are. Okay, now we need to make our table of properties and energy transfers. So let me do that. Okay. Oh, I hear some more thunder out there. Oh, I just heard a big one. How about you guys? I don't know where you guys live, but are you hearing any thunder? If you can hear some thunder, unmute and tell me, would you? I'm just curious.
I hear a lot of thunder where I'm at.
Okay, where are you? Where are you located?
About 51st and Union.
Okay, kind of on the west side over there, right? West of the river?
Yep.
Okay, well, it's probably coming my way. I'm east of the river, but I'm back in Tulsa. The last two times I visited with you guys, I was in Chicago, but I'm back now. Got to see my some of my kids and grandkids. It was fun. Okay, now let's write in anything we know here. We know the inlet state is 500 Rankine, so that's state one. So we're going to put 500 Rankine here. We'll put that in parentheses so we'll know it's a unit. And 10 psi. Well, we can put that right here. 10 psi. All right, guys. P1V1 is equal to RT1. I want you to find the V now. I'm going to shut up for a minute. I know you can do this. We've done it many times before. I'm going to do it. But see, you need to know how to do it. I got to make sure you know how. Okay, go for it. You got a minute. I'll be quiet. I want this little V here. We know P, we know R, and we know T. So find V. Well, I got an answer. I'm always picking on you, Stuart. Stuart, are you still working on that, or do you think you know what that little V is?
I'm still working on it.
Keep working. That's fine.
I have a question real quick.
Yeah. Go ahead.
So it's for the R value we use, what table do we find that on? Because the 0.287 is for metric.
Yeah, don't use 0.287. Let me show you where that is. It's a good question. Probably in the English
F.
pages.
Yeah.
Okay, I'm finding it now.
Is it F.4?
Yes, it's
Okay.
table F.4 and it's 5334. Do you see it there?
Yes.
There it is.
All right. Thank you.
Anytime. Well, I got an answer. Let's go to my friend Spencer. Spencer, have you got the answer yet? Or was that you I was just talking to?
It was.
Oh,
Give me
well,
just 1 sec to plug things in.
yeah.
2667.
Spencer, you got to divide by 144.
Oh, to get it to inches
Yeah,
squared.
yeah. Well, here, let me write it out.
It's like 18.52.
Yeah, that's it. 18.52. See, now that's cubic feet per pound mass. Cubic feet per pound mass. Now, if anybody wants me to, I'll write it out. But somebody's going to have to say, please do. I'm listening.
Please do.
Yeah, okay, let's write it out. Here we go. See, that R is 5334. And the units are foot pounds per pound mass, temperature, pound mass Rankine, temperature is 500 Rankine. There's your V1. Now that's in cubic feet per pound mass. Put some brackets around there. There we go. And the pressure is 10 pounds force per square inch. I'm running out of space here, but see, you have to multiply this side by 144 square inches per square foot. If you do that, then on the right, you'll have foot pounds per pound mass. And on the left, you'll have foot pounds per pound mass. Because see, the square inches cancel. And the cubic feet will cancel the square feet, and you'll just have foot pounds force per pound mass, because this is cubic feet per pound mass. Did that make a lick of sense to anybody? I'm hoping it did. That's what you have to do to get the 1854. Or no, 1852. You had to divide by the 144 for the units to be the same. Okay, I'm going to erase that now. I've shown you how to do that. Okay, well, we're doing great. Let's keep on going. Now, if you read this problem, it says it has a compression ratio of 10 to 1. What that means is the V1 over the V2 is equal to 10. It's 10 to 1. The V here at V1 is 10 times the V here at V2. I didn't exactly do that to scale, but these scales are logarithmic anyway. They're not linear. And so, hey, I can do this practically in my head. I can divide by 10. This will be 1.852. I just divided by 10. See, we know V1. And so you can solve for V2. All right, great. Now what? Let's keep reading here. Let's see, inlet state, fuel added is 600 BTUs per pound mass. And where is that? You know what that is? That's the Q23, isn't it? Let me write that down someplace. The little Q23 is 600 BTUs per pound mass. Right? Now, where does that go? Well, that goes right here. It goes right here, 600. These are BTUs per pound mass. Okay. Well, so what? Well, I don't know. Do we know anything else? Let me keep reading. The network, how much power, inlet state is la, la, la. I think that's about all that we know here. Now they did give us the total displacement. We can talk about that later, maybe. But I think we got a lot of information here already. I know what V4 is because, see, little v4 is the same as little v1. So I can put that in here. This is going to be 1852. If you don't understand that, just unmute and ask. And see, little v2 and little v3 are the same. So I can put those in there. That's 18 or 1.852. Everybody happy so far? Okay. Now what? Well, since this is a isentrope, there's a lovely equation that I derived for you guys one day. It goes like this. I know I derived this part of that equation, and I showed you how you can get to there. It was using one of those Gibbs equations, and we derived those from scratch. But this is a nice equation, but you can only use it on an ideal gas isentrope. But that's what we have. Going from 1 to 2 is a reversible adiabat. It's an isentrope. And so we can use it. I especially want to use it here because, see, I know what V1 over V2 is. It's 10. They said it was 10. That's called the compression ratio. So we're going to do that now. I might have told you that the Otto cycle is a theoretical thermodynamic cycle for the gasoline engine. We're talking about the gasoline engine, like you have, most of you guys have a gasoline engine, unless you have a diesel or a hybrid or a, what's that one that's electrical, Tesla or a Prius maybe? Okay, well, here we go. We're going to plug this in. I'm going to put the numbers in now, and I'm going to get T2. See, T1 is 500. Now we know it's Rankine, but see, this is V1 over V2. Well, that's 10 to the K minus 1. I can do that. So I'm going to do it now. I'm going to take 10 to the 0.4 times 500. Okay, I'm getting pretty hot temperature at state 2, 12. I think I'll just round it off. I'm getting 1256 Rankine. And I want to know if that's what you guys got. I might have Googled. Did you get
I
that?
may have missed it. Where did you get the K value from?
Oh, it's air. We're
Oh,
dealing,
right.
we're dealing with air. I'll show you in the book where that is if you need me to. Let me see if that's what I got when I did this before. This is problem 10117E, and I'm getting 1256. Yeah, that's what I got before. I think we're doing great. Oh, looky here. P2V2 is going to equal RT2. So now that we have V2 and T2, we can find P2. I think I'll give you another minute. Looky here, we have R. Well, I just had it on the board a second ago, and we know T2, and we know V2. We can find P2. I'm going to shut up now, and I want you to find P2. Go for it. And I'm going to do it. We'll see if we agree. And I think it was Spencer that forgot the 144. Don't forget the 144, Spencer. Was it you that forgot the 144?
It was, but I didn't this time.
Good going. What do you have an answer? What'd you get?
251.2 psi.
That's what I got. It's exactly what I got. We're doing great now. Now what? Well, I don't know. We got some more boxes to fill in, that's for sure. Hey, now wait a minute. Two of these little Q's are zeros. Which ones? Let me go to one of my excellent students here. Cameron, I want to know which of those Q's. There's a couple of these Q's that are zeros, Cameron. Which ones are they?
The top one and the one under the 600.
You got it. The reason is those are adiabats. It's an adiabatic compression from 1 to 2, and it's an adiabatic expansion from 3 to 4. No heat transfer. Okay, great. Now, Cameron, as long as I got you on the phone now, two of these little W's are zeros. Which ones are the zeros, Cameron, on these little W's?
The second to top one and the bottom.
You know, I think he's starting to get it. Cameron, you're starting to get it because, see, from 2 to 3 is an isochore. It's an isochore. And 3 to 4, or 4 to 1 is an isochore. So yeah, so we did good there. Now, what else can we do? Hey, let's do something with this 600. Now, let me think about this, the 600. Don't know what to do with that. The 600. How about you guys? Do you have any suggestions? We got some empty boxes here. Do you have any suggestions there? Well, nobody said anything. I'm just going to try some things. Guys, try some things. If it doesn't work, try some other things. How about this? going from how about this? We'll just try this. The change in specific internal energy from 2 to 3, we'll put a 2, 3 there, is going to equal the C sub B T3 minus T2. Well, nice idea, but see, I don't know what T3 is. I can look up this CV thing, but I don't. But now wait a minute. Wait a minute. I got another idea. This is equal to Q23 minus W23. Okay, now let's circle the stuff we know. Oh, look here. We know Q23, and we know W2. Oh, look at here. Hey, I could figure this delta U. It's going to be, well, it's going to be 600, isn't it? Can y'all, little Southern talk, y'all see that delta U is 600 because it's 600 minus 0. Well, that's 600 minus 0. It's 600, yeah. Now look here. If this is 600, you know, I almost wrote kilojoules. We're not doing kilojoules, are we? Forget the kilojoules. That's no good. That's, you know what that is? That's BTUs. It's BTUs per pound mass. Okay, well, we got 600 BTUs per pound mass equals C sub B. Now you can look that up. I just happen to have it memorized. It's 0.171 BTUs per pound mass Rankine. We probably should go look that up. Go to the back, and was that table F4? Is that what it was?
Yes.
F4, okay, let's see if we can find that. For air, it's, yeah, I got it right, 1.171, yeah, that's right. And then T3, see, I don't know what that is, but T2 is 1256. Okay. Hey, we can solve for T3. Do you see it coming? All right, well, here goes. I'm going to solve it. I want you to work along with me now and see if you can get the T3. There's the equation. I know you can do this. Okay, I got an answer for T3. Wonder if this shows up on, yeah, it should. I'm getting 47, I think I'll round off, 47.65, that's pretty close. 47.65. Let me see if that's what I got when I did this before. 47.65. Yeah, that's what I got before. I think we're doing great. I need one or two students to confirm that. Anybody getting that?
That's what I got.
I bet it's right. And the units, what are the units? The 47.65. Anybody know the unit?
Degrees Rankine.
Yeah, they're Rankine. They're degrees Rankine. It's absolute temperature in the English. Really, it's British engineering is what it is, but we'll just call it English. Hey, now look here. Look here, P3 V3, let me write that. P3 V3 equals RT3. Now we have T3. We have R. And look here, we have V3. And we're not going to forget the 144. And we can solve for P3. And I'm going to do it. I want you to do it. And then I'll pick on one of my more brilliant students, and we'll see what we get. Here we go. I think I hear rain now, but it's sort of a gentle pitter-patter. Hey, I got an answer for P3. Let me go to one of my more excellent students. But we'll give them another minute to think about it. Bear, you got that done yet? Bear, unmute.
I do not have it ready yet.
Keep working. We're doing P3V3 equals RT3. Well, how about my friend Aubrey? Aubrey, yeah. Did you get it yet?
I got 953.04.
I got 953.04. Is that what you just said?
Yep.
That's what I got. Why don't we just call it 953? That's pretty good. Hey, we're making progress here. What are we going to do about these empty boxes here? Well, I got an idea. Let's try this. I'm gonna erase all this if that's okay with you guys. If it's not, speak up quick, because I'm gonna erase this because I need the space. I'm gonna erase. Too late. You didn't say anything. I'm gonna erase this now. Adios. There we go. Okay, now this may or may not help us. It's worth a try. Here goes. This isentrope, adiabat, from 3 to 4, we can go T4 over T3 is equal to V3 over V4, which, you know what? That's 1/10, isn't it? To the 1.4 minus 1. I like it a lot. I can do that because I know what T3 is. We can solve for T4. Here goes. We are going to solve for T4 now. And I'm doing that. Okay, I got an answer for T4. I wonder if it's what you got. Did anybody get 1897? I rounded off there. And I'll wait till I hear two students tell me that's what they got. Maybe I did it right.
That's what I got.
There's one.
I got.
Well, that's two. I think we're in good shape. Hey, now look at here. We have P4 V4 equals RT4. And we know T4. Somebody had a comment. We know V4. We know R. We can find P4 if we can remember to divide by 144. I'm going to do that now. And I'm going to find P4. Here I go. I hear rain pitter patter on the roof right now at my house. Well, I got an answer. I don't know if it's right or not, but it looks reasonable. I'm getting P4 is 37.9 PSI. Anybody getting that?
That's what I got.
I bet it's right. So we're doing great. Well, we got a few more boxes to fill in. Let's fill those in. For anybody just tuning in, we are doing an auto cycle. It's problem 10.117E. E stands for English. We've got to know how to work in English and metric. Metric's a lot easier, but we got to work in both. Okay. Does anybody have any idea how to go about getting any of these other boxes? I'm listening for any ideas to come up with these. We got some missing boxes here, and I'm listening for any ideas. I don't hear any ideas. Okay, well, one way is we could do this here. I'm going to erase this now. I need some room. Unless there's a question or a comment. Well, nobody said anything. How about this? See, if you want a delta U from 1 to 2, for instance, all you got to do is put in the C sub V, which I think we looked up. It's the 0.171. And see what this is T2 minus T1. There you have it, and you can get your delta U. Okay, here goes. I'm going to do that. Well, I got an answer. I got 129.3 rounded off for the delta U going from 1 to 2. Hey, you know, while we're at it, I could put the isotherms on here. See, we figured out T3 was 4765. Let's put it in. Here goes. This is the 4765 Rankine isotherm. There. What about T4? T4. Well, we could put that in too. Kind of messy there, but that what that is the 1897 Rankine isotherm. Yeah. And then finally we have a 1256 isotherm. That's coming here through like this. That's the 1256 Rankine isotherm. And notice that the adiabats are steeper than the isotherms. I think I've told you that. Adiabats are steeper than isotherms. Okay, well, we're doing great. Let's go ahead and get these in. These are the same doggone thing. You go delta U from 3 to 4. Delta U from 3 to 4 equals 0.171 times T3 minus 600. Okay. And so you could get delta U from 3 to 4. Here goes. I'm going to do that. Now, wait a minute. No. It was a wonderful idea. No. We know what that is, don't we? Yeah, never mind. We know what that is. That's the 4765. Yeah, we can do this. $47.65 minus 600. Well, I got an answer. I wonder if that's right. I'm getting 712.2 BTUs per pound mass.
Why did you use 600 instead of the temperature at 1256?
I'm wrong. No, wait a minute. Wait a minute now. I'm going from 3. I'm trying to go from 3 to 4, right? And
Right. So it should be 4 minus 3.
This was wrong. Now was that Spencer just now?
Yes, sir.
Spencer, I think I'm going to owe you a thank you point. I'm going to put it up here, Spencer. Proud of you. Going from 3 to 4, Spencer, don't I need 1897 minus a 4765? What do you think, Spencer?
Sounds right to me.
So I did something wrong there, but because Spencer's awake, even though it's Monday morning, he helped us all out. And I do appreciate it. Okay, now let me try that. Okay, well, I got an answer. I'm getting a negative. Interesting. Going from 3 to 4, I'm getting a negative 490.4. I wonder why it's negative. Because you're cooling off. Going from 3 to 4, you're getting colder, aren't you? That makes sense. See, when you get colder, what do they call that? The specific internal energy gets smaller. It's negative. The change is negative. We did great. Okay, hey, we can do the same trick from 4 to 1. Here we go. 4 to 1 is the 0.171 times. Well, now that would be 500 minus 1897 from 1 minus the 4. Okay, here goes. Let me do that. Well, I'm getting a negative 238.9. Now, if that's not right, speak up. Let me know. Now, if you added all these up, you're supposed to get 0. Because, see, what do they call that? Specific internal energy is a property. And if you add up all the changes in a cycle of a property, you should be back to where you started. So the changes should add up to 0. I'm going to add these up. They don't necessarily look like they add up to 0 to me, but I'm going to add them up. Here we go. 129.3. I'm adding these up. Plus 600 minus 490.4 minus 238.9. Holy cow. I'm getting 0 when I add those up. I'm getting 0. I think I've told you guys that. If you take the sum of all the changes in temperature, let's say, for a cycle, you get 0. If you take the sum of all the changes in, well, what did we just do? Specific internal energy, you get 0. In fact, if you take the sum of the changes in any property over a cycle, they should add up to 0. Now these are not properties. Heat transfer per mass and work per mass are not properties. And if you add those up over a cycle, you will not get 0 because they are not properties. But look here, we can get these. Let's go ahead and get those. I need some room here. So I'm going to erase this if that's okay with everybody. Any comments or questions so far? Well, nobody said anything. All right. Now on these, the way it works is, this is a cylinder piston thing. It's a control mass. And the first law for a control mass goes like this. You guys know that. You've memorized that. And look, we know this. We're going to go from 1 to 2. And we know this. Hey, we can find the work per mass. You know what I think it is? I think it's a minus 129.3 BTUs per pound mass. Minus 129.3. Can you read that? And I hope so. Well, we only have 2 more boxes to fill in. And this one here, we could do the same thing, only we're going to go delta U from 3 to 4 is equal to the heat transfer per mass from 3 to 4 minus the work from 3 to 4. So this one here, this is going to be plus or minus 490.4. Now let me call on one of my wonderful students. Let's see who I want here. We'll start over again. Stuart. I'm always picking on Stuart. Stuart, this here work from 3 to 4 on this adiabat is either plus or minus. Now you have a 50-50 chance of getting this right, Stuart. Is it plus or is it minus? Going from 3 to 4 the work.
Positive.
Yay, good going, Stuart. Now the reason for that, Stuart, I bet you know. You tell me the reason. How come it's plus, besides the algebra, of course, but if you're going from 3 to 4, why is the work positive, Stuart?
Because Q is 0.
Well, I would accept that. But what I wanted you to say, have you ever noticed instructors, teachers, they have stuff that they want the student to say. What I wanted the student to say was, Mr. Griffin, from 3 to 4 is expansion, and expansion work is positive. Have I ever told you guys that? Expansion work is positive, compressive work is negative. Well, that's expansion going from 3 to 4. Look, you got bigger. See, the V's got bigger. It's positive from 3 to 4. Look, it's negative from 1 to 2 because 1 to 2 is compression. Compressive work. Here, let me write it. So some of you learn with your eyes. And so I'll write it. Compressive work is negative. Ta-da! There, now you've seen it written in letters. Compressive work is negative. You'll never forget it. I've told you that many times, and I want you to get it. All right. Hey, look, we filled in the whole chart here. Now, let's add, wait a minute. Ooga, we didn't get this one. Now, this is either going to be plus or minus 238.9. I was picking on Stuart the last time. Stuart, you got another 50-50 chance, Stuart. This is going to be plus or minus 238.9 from 2 to 3. Heat transfer per mass.
Minus.
Don't go to the casino, Stuart. It's positive. Heat transfer going in is positive. Heat transfer going out is negative. So it's going in. Can you see the heat going in? See, this is your cycle, and the heat transfer is going into your cycle. See, if you drew it like this, now let's put a plus there. Remember that schematic that I told you guys, and you drew some for me? It goes like this. You have see, this is a heat engine. It's a gasoline, it's called the Otto cycle. This is the low temperature. This is the high temperature. Hope you can read my writing. And we're going around. Hey, did you notice it goes around clockwise? Do you see that cycle? It's clockwise, isn't it? See, on the schematic that I told you guys to draw, it goes like this. Now, we usually have big letter with the dots on them, but we could have little letters. That'd be okay. Have little letters. And see what this little letter is here is little q 2, 3. And what this little letter is here is little q 4, 1. See, in Q23 is 600. And we'll have a little w here. And little q 4, 1 is 238.9. Now, what little w is the net work. Now, to get the net work, you have to add these up. Let's do that algebraically. 490.4 minus 129.3. I'm getting 361.1. Okay. Well, that should be little w. It should be 361.1. When you add up the little q's, let's see what you get there. Well, when you add them up, you get 600 plus, now wait a minute, 4 to 1 is a minus. This one here from 4 to 1 is a minus. Am I the one that put a plus on there? Shame on me. 600 minus 238.9 is 361.1. These add up to the same because the sum of all the Q's is equal to the sum of all the W's. Did I just tell you the opposite a little while ago? I hope I didn't tell you that. Because see, this is the original version of the first law for cycles. For a cycle, if you have a cycle, the first law, that the way it was originally discovered was that the sum of all the heat transfers is equal to the sum of all the works done. And hey, they added up the same. That's good. That's good. Oh, I think I remember what I told you. Yeah, now I remember. I told you the sum of all the changes in properties gives you 0. Well, you don't get 0 here. The sum of all the heat transfers don't give you 0. That's not a 0. And the sum of all the work, in this case, work per mass, that's not a 0 either. See, you don't get zeros when you add these up. But you do if you added up the changes in any of the properties, you get 0, but not the heat transfers, because the heat transfer and work are not properties. I don't know if that made any sense, but that's a fact. Now let's get the efficiency. Let's do that. Do you remember how to do the efficiency? There's a little room right here. I could do it right in here. The symbol for the efficiency is a Greek letter eta. I think it's the 7th letter of the Greek alphabet. Let me count them. Let's see. Alpha, beta, gamma, delta, epsilon, zeta, eta. Yeah, it's the 7th. Eta is the 7th letter of the Greek alphabet. And it's the efficiency. And the efficiency here would be the desired output. And for a power cycle, it's the 361.1. And what goes here is something that costs you. Well, what costs you is the 600 heat transfer per mass. You got to pay for that. That's like gasoline. If it's a gasoline engine, you got to buy the gas. It costs you money. Okay, now we're going to get the efficiency. Here we go. 361.1 divided by 600 is 0.6018. What? 60%. 60%. Keep in mind, you're not going to get that with your car because your car is not, all the processes are not reversible. There's friction and all sorts of other irreversibilities going on in your car, and you're not going to get anywhere near 60% efficient for your car. Now, they also wanted something else for the network, how much power is produced. Well, I could show you that. Need a little room here. But before I do, talking about the power produced, is there any question from anybody? Any comments or questions from anybody? Okay. Well, all right. I just need some room to work here. I guess I could erase some of this. And we could erase this schematic here. See, these add up to 0, but these don't. They don't add up, but they do add up to the same. Isn't that interesting? They add up to the same. Before I talk about power, there's a thing that I taught my students a few semesters ago called checking your work. Let's do that. Now on these processes going, say, from 1 to 2, we're just going to look at process 1 to 2 for a minute, and we're going to check our work. It's not a bad idea to check your work. We have an equation for the work per mass going from 1 to 2. It goes like this: P2V2 minus P1V1 all over 1 minus N. In fact, we derived that equation from scratch. I don't remember what day that was, but we did. And the thing is, we already have the answer. It's negative 129.3 BTUs per pound mass. But we didn't get it doing this equation, did we? Well, let's do it with that equation. Is just checking our work to see if we did stuff right. Okay, now, being lazy, instead of going P2V2, could I go RT2 minus RT1? Yeah, that'll be a little easier for me. And we know what N is. See, N is equal to the 1.4 for air because it's equal to the K. It is a polytropic process. See, isentropes, if you have an ideal gas, the polytropic constant is equal to that K in this case. And K's got a fancy name. It's called the specific heat ratio. Remember, here's what it is. The specific heat ratio is the ratio of C sub P over C sub V. It's 1004 divided by 0.71. No, I'm in English, senor. It's 0.240 divided by 0.171. But it's the it's the same ratio in SI. If you used SI, you would have 1004 all over 0.717. Put, just to be sure I'm not lying to you, put those in your calculators and see if you get a 1.4. Let's try it. By Jove, that one worked pretty good. Let me try this one. By Jove, that one worked pretty good. Excellent. Well, now we're going to plug this stuff in and see if we get negative 129.3. This is called checking our work. Okay. Let's make some room here so I can. Any comments or questions? I just need some room to work here. Here's some room right here. I'll make some room. We're doing process 1 to 2. And we think little w is going to equal this. And remember what R is. It's 5334 foot-pounds, force, pound mass, Rankine. T2 minus T1, well, that'd be 600, no, it'd be 1256. I need the space. It's equal to 1256 minus 500 Rankine. Yeah. All divided by 1 minus 1.4. Yeah. And now here's the catch. This is in BTUs per pound mass. So you have to multiply all this by a BTU is 778.17 foot-pounds force to get BTUs per pound mass. See, the Rankines cancel. Okay, we're going to plug all this in now. Those of you that are with me on this, and see what you get. Well, I'll tell you what I got. When I did all that, I got negative 129.6. Now, what we were supposed to get is negative 129.3. So somewhere I rounded off. I think I rounded off a lot of these numbers. You remember, I just lopped off some numbers. If you kept all those numbers in there, like probably you should, I think we're okay. That confirms me that it's called checking our work, and we found the work per mass using a totally different method. How did we get this? We used the first law, didn't we? We didn't use that. That's not the first law. And we checked our work. Now we could also bore you out of your gourd and check the work going from 3 to 4, the 490.4. Wouldn't that be fun? I'm sure you're just anxious to do that. But I'm being lazy. I don't think I'll do it. You could do it though. It'd be good for you. You could plug in this same equation going from 3 to 4. It's an adiabat. It's polytropic with K equals 1.4. And if you're very lucky, you should get 490.4 or bang close. Before I go on, is there any comment or question? Did I go too fast on that? Well, okay, I guess you're happy. If you're happy, I'm happy. All right. Well, let's answer the question. They wanted something about the power. Let me read this. If you just woke up from a daydream, we're doing problem 10, 117E. We have filled out this property and energy transfer table completely. We found the efficiency. You know, I don't think we found the mean effective pressure. Did they ask for it? Let me read this. No, they didn't ask for that. They wanted something about the power. We can do that in a minute. But here, let me erase this and we'll do the mean effective pressure, unless you have a question. We probably ought to do this 490.4. Here, let's do that, and then we'll do the mean effective pressure. Okay. If you wanted the work going from 3 to 4, then what you'd need here is different numbers, right? Going from 3 to 4, what you'd have in here is 1897 minus 4765. Okay. All the rest is the same. Do that and see if you get the 490.4. I'm going to try it. Here goes. Let's see what happens. Doing all that, I didn't get 490.4. I got 491.5 BTUs per pound mass. But again, I think I'm all right. We're off. We're off by a whole BTU per pound mass, aren't we? But I think I rounded off. These are, I rounded off stuff there. I think we're okay. We checked that. Now let's do our mean effective pressure, unless you had a comment or question. Nobody had a comment or a question. Okay, we're going to do a mean effective pressure now. We found the efficiency was 60%. You know what we didn't do? We didn't do a TS diagram. Now, wouldn't that be fun to do a TS diagram? That'd be fun, wouldn't it? Hey, maybe we can. Hey, what a great idea. But first, I wanted to show you the mean effective pressure. Now, the formula for mean effective pressure is your network divided by your delta V from 1 to 2. Now, the network is 361.1 BTUs per pound mass. And the delta V from 1 to 2 is it's 1852 minus 1.852. cubic feet per pound mass. Now, if you put that in your calculators and get a number, it's not going to mean anything because the units aren't right. If you're going to do mean effective pressure, what you want is PSI. You want PSI. Well, whatever this is, it's not PSI. Look, it's the, can you see the pound masses will cancel? But it looks to me like you got BTUs per cubic feet. That doesn't exactly equal a PSI in my book. So we have to convert that. Well, let me show you how to do that. To get rid of the BTUs, you do this. You go 778.17 foot-pounds force is equal to a BTU. Now let me make sure that's right. Let me look that up. Go to the back of the book and shop around and look under pressure. And it says a BTU. Having trouble finding that. All right, well, let me keep looking here. Trying to find the BTUs. Oh, no, I'm looking in the wrong place there. That's not pressure. That's, I had a senior moment. You know what that is? That's work, isn't it? Or energy. Yeah, here we go. It's energy. Hey, that's right. I found it. It's on table table A.1. It says a BTU is 778.17 foot-pounds. It's on table A1. I found it. Yay. Well, that's good. I can see the BTUs cancel, but we still have a problem. We want pounds per square inch, and we don't have them yet. Can you see you got square feet because you have a foot here and a foot cubed here? That gives you square feet. So here's what we're going to do. We're going to multiply by 144 square inches is a square foot. Wait a minute, I'm doing it the wrong way. The square foot are in the denominator. Uh-oh, got to do it this way. A square foot is 144 square inches. Okay, now we're gonna put all this into our calculator, and we're gonna get the mean effective pressure. All right, on your mark, get set, go. Do it for me, and we'll get the mean effective pressure. Here goes. I must have done something wrong. Let me start over here. Yeah, I got it. The mean effective pressure is, let me call on one of my wonderful students here. Let me wait a minute. They probably aren't done yet. Well, let me see if Bear's got that. Bear, do you have that mean effective pressure yet?
No, I'm still plugging in a couple answers or numbers.
Well, it's okay. Just plug away. Take your time. What about my friend Aubrey? Aubrey, do you have that mean effective pressure yet?
I got 117.07.
That's what I got. I got 117 PSI. Now that's the mean effective pressure. Guys, that is not the average pressure. To get the average pressure, what you'd do is you'd add these all up and divide by 4. Let me do that just for fun. 10 plus 251.2 plus 953 plus 37.9. Yeah, those all up and divide by 4. The average pressure is not the 117. I'm getting 313 PSI. That's the average pressure. This is the mean effective pressure. Why is that smaller? The reason is you see this 953, that's the peak pressure at state 3. It only exists for just a fraction of a moment. It's just a very momentary, fleeting thing right there. When the gasoline explodes, gets the piston, the material in the piston gets real hot, and the pressure just skyrockets. But it's only there for just a second. Then it expands. It cools off. The temperature goes down. See, at 3, the temperature was 4765 Rankine, but at 4, it's 1897 Rankine. It cools off, it expands, and the pressure goes way down. It was 953, but it goes down to 37.9 in a hurry. They've developed this thing called the mean effective pressure, and they design engines using it rather than the average pressure. So I don't know if some of you go into automotive engineering, you'll know more about it than I do. Okay, well, and the last thing here before our break time is they wanted us to calculate the power. Yeah. What's the net work in the cycle? We did that. How much power is produced? Okay, well, let me make a little room here. And we'll see if we can do that. I could talk about this for probably a half an hour, but we don't have time. We got to get onto the diesel cycle here in a few minutes. But let me show you how you can go about getting the power. Now, what they're talking about is big W dot. The name of that is the power. And I tell you what that's equal to. That's equal to m dot times, well, we're talking about the net power for your cycle. If you knew the m dot, or the mass flow rate, and you multiplied by this 361.1, you could get your net power for your cycle. Now, how would you go about getting your mass flow rate? Well, they give you some interesting facts here. they give you the RPM. Here, let's write that down. It's 2100 RPM. Well, I don't really want RPM. I want revolutions per second. So here's how I could fix that. A minute is 60 seconds. See, this is revolutions per minute, and a minute is 60 seconds. So if you divide the 2100 by 60, you get 35 revolutions per second. That makes sense? Now, the thing is, this is a 4-cycle engine.
Shouldn't you multiply by 60?
Well, here, let me write it. Now, was that my friend Stuart?
Okay, I see where it went.
Oh, you figured it out? Was that Stuart?
Yes.
The Stuart that got this honking thank you point earlier?
I think that was Spencer about it earlier.
Oh, that was Spencer. Okay, well, that's fine. No, I think I did that right, Stuart. But for the rest of you here, if you'll write this revolutions per minute, then when you multiply by minutes is 60 seconds. Can you see that the minutes cancel? And that's what we wanted. So I think I did that right. And here's what I was going to tell you. This thing is, it got 35 revolutions per second, but it's a 4-cycle engine. Remember, it goes compression, ignition, power cycle, exhaust, and then it goes compression, intake. No, wait a minute. Let's see. I'm getting fouled up now. Compression. Well, where's the intake? Oh, that's here. It goes compression, ignition, power cycle, and then the exhaust. But then there's another complete mechanical cycle. And during that mechanical cycle, you have the intake of the gas, and then you have, I'm getting mixed up now. Let me think this thing out now. Let me draw a piston and go through that. We got all that there. We're gonna move on to the diesel cycle, but I just want to talk to you about the 4-cycle thing here. Here's your piston. Now in state 1, you've got your piston here. State 2, you've got well, state 2, the piston's way the heck down here. You got compression. And then what happens? Well, I really need to draw these pistons the way they really are. They're really like this, you know what? You know what I'm talking about? This has this is going round and round. And then up here is it's up here. And it's more like this. And then what happens is you have your power stroke and it goes back down to here. Our artist's rendition of what's happening here. And then this is state 1, 2, 3, 4. And then compression, yeah, okay. And then there's valves up here. And this is an intake valve, right? And you have, I don't think I did that right. You've already got the intake. There's 2 valves up here. And you're coming up here and there's a spark, blam, and that pushes this down, and your inertia turns your flywheel all the way around, and you come back to where you are here, and you're oh gee, I'm taking up all your valuable time here. Which way are we going? We're going this way, yeah. So where is this one? It's like this. So it's down here, right? This is more, it's kind of up here someplace. This one's down here. And we're turning. Yeah. I think I'm turning the wrong way here. Okay, we're turning this way, yeah, okay. And then we're down to here, and then we're turning this way here. Okay. The gas is already in there, and then there's a spark plug, and the spark plug ignites that, pushes it down. Inertia continues to rotate the flywheel there. And then what happens is you repeat the whole thing over again. I'm running out of space here, but as this thing, the inertia pushes it back up, the exhaust valve opens up, and the exhaust pushes the rotation. Let's see now, where are we at now? We're here again. Yeah. The exhaust valve pushes the exhaust gases out. The engine has to turn over twice. The engine has to turn over twice. It's called a 4-cycle engine. So you have the intake, compression, ignition, power, and then you have the exhaust, and then you have the intake, compression, ignition, power. It goes around and around 4 times. So what did we come up with? 35 revolutions per second. That's what the engine is doing, but there's only 17.5 revolutions per second providing you with power. I don't know if that made any sense. Because the exhaust and the intake, they're not providing any power. And so you only get power on 17.5 revolutions per second, not the 35. So we could talk about the time involved for one complete energy producing cycle, and it would be 17.5 seconds. And we could get our m dot that way. Remember, I had the equation W dot equals m dot times little w, and we have little w. And if you're trying to find the power, you need this. We can get that from the RPM. They gave us the RPM. And we also know the specific volumes. They gave us, here's what they gave us. They gave us delta V. And they said on this problem, if you'll read it, it says a total displacement of 75 cubic inches. And what I'm telling you is delta, see V is equal to M times little v. And so delta V is equal to M times little delta v. We know what little delta V is. It'd be the difference between a V1 and V2. And they give us this. So we can get the mass entering the piston during every revolution that happens 17.5 times a second. We could get the m dot and we could solve for the power, but I'm not going to ask you to do that on a test. If you can fill in these boxes, get the mean, the mean, what do they call it? The mean effective power, MEP, and the efficiency, I'll be very happy. I think that's enough of that. I'm tired of that problem. I'm going to go and talk about a diesel cycle, but we're going to take a little 10-minute break. And then we're going to talk about the diesel cycle. Let me see which one I want to do. You're going to be given some homework. And I thought since you guys show up for class, we could do one of your homework problems together. And so if you just take good notes, you'll be, I think I gave you 2 homework problems. I don't think they're due for a few days. Let me tell you what they are. But now this applies also to the people that tune in on YouTube. Yeah, they're 1072 and 1074. So if you tuned in on YouTube, I'm going to do 1072 for you. So if you'll make a copy or write down 1072, we'll do it together after our break, and you'll be halfway through with your homework assignment. Then all you have to do is 1074. Okay, that's what we're going to do. But right now we're going to take a 10-minute break, and we're going to come back and we're going to do the diesel cycle. Go stretch. I'll be back in 10 minutes and we're going to do the diesel cycle. All right, go stretch. We'll be back. Well, welcome back, students. Now we're going to do a diesel cycle. It's problem 1072.
Before we do that, I have a quick question.
Yeah.
So last week I noticed that we had a homework assignment in Unit 3 that's supposed to be due today. That's no longer posted. So I don't know what number problem / problems that's supposed to be.
Well, I can tell you, this is my friend Spencer.
Yes, sir.
Okay, Spencer. There's problem 965 was, I think, due today at in the middle of the night, and it's no longer posted, and so I'll give you some late credit if you turned it in on that's the one, pretty sure. And Spencer, let me look at your grades here. Yeah, that's it. It's 965. Do it and turn it in on what am I trying to say? On the
Shouldn't it be due tonight though, like at midnight? Because all of the homework assignments are due the day of the next class.
yeah, my IT person. Yeah, turn it in on email. I'll try not to be too unkind. But my IT person switched on you guys and went from 11:59 to 12 o'clock midnight, and that completely fouled several of my students up.
Yeah, when that was never communicated to us.
No, well, it was on Blackboard. If it said, what is today, the 13th?
Right.
If it said the due date is 12 a.m. on the 13th of July, that was last night. It's on there. It's just that you must have thought that it was going to be midnight tonight.
I hadn't looked at it because I had assumed that it would be due tonight at midnight and fall in keeping with all the other assignments.
Yeah, my IT person, who is a wonderful person, don't get me wrong, but she, for some reason, switched to 12 a.m. instead of 11:59. But there's a big difference between the two if you have the same date.
Yeah, full 24 hours.
Yeah, there's 24 hours. So turn it in on the email, and we'll try to be okay with it. We'll be all right.
Will that be the standard? Will that be the standard going forward? Because the next assignment says it's due at 11:59 on Wednesday. So is it switching back, or is it going to be midnight from now on? I just wanna-
I'll have to check on the homework, but for heaven's sakes, don't screw up on the final. We only have 2 weeks of school left. Did you know that? We have this week, we have next week, and that's it. So I'll try to not confuse you anymore, but it's there. If you read it, it tells you exactly when it's due. And if you turn it in after it's, well, you can't turn it in on Blackboard after it's due, it's gone.
Right.
Yeah, it's gone. So I give you time. I think I give you, I don't know, 48 hours or even more to do your stuff. Don't wait till the last minute. Okay? Okay, now we're going to do 1072. And it's a diesel cycle. And let me find it in the book here. I need to tell you what a diesel cycle is. It's got 2 adiabats, which are isentropes. It's got 2 isentropes. It's got 1 isobar and 1 isochore. It's a little bit different. So it has isentropes, an isobar, and an isochore. And here I'll draw you the PV diagram. Hey, you know what? We never did do the TS diagram on that last one. Shame on us. That would have been so much fun to do that TS, but it's too late now. Oh well. Okay, now on the no, let's do a PV. I was thinking that we didn't do the TS on that other one. Maybe we can do the TS on this one. We'll see. Okay, now let me find it. 1072. 1072. Now your homework, I think, is 1072 and 1074, but we're going to do this one together. Isn't that nice? Yeah. I think we got time. We'll just get this one done. 1072. Hang on. Almost there. Yeah, here we go. 1072. Yeah. I find it. Diesel engine has an inlet of 95 kilopascals, 300K. All right. Well, let's do the 300K. Now, here's the 300K. I can make this a little bigger, maybe. Let's see. Let's see if I can make this a little bigger. All right. And we're going to do the 300K here. There's your 300K. But see, our process from 1 to 2 is an isentrope. It doesn't follow the isotherm. It follows, it's steeper. It's an adiabat. It goes like this from 1 to 2. It goes come on now. It goes like this, and up here like this. Yeah, there you go. From 1 to 2. That's your compression stroke. And then your burn, you have an isobaric burn that goes like this. Here, let me make this a little bit different. Let me fudge this just a little bit more here. There we go. And you have an isobaric burn to state 3. And then you have another what's the word? Isentropic expansion to state 4. And then you have the exhaust intake from 4 back to 1. This is state 1 here. There's state 1. And see, that red line there is your 300. That's your 300K. You guys will be happy now we're in SI again, and you don't have to fool with those BTUs and that confusing English stuff. Okay, so let me keep reading here. We're doing problem 1072. And let's see, I got lost. Okay. The inlet is at 95 kilopascals. Well, we could put that right here. That's 95 kilopascals. All right. And 300K. Let me make that 300K again. I had it there. This is the 300K. 95 and 300K. Okay, then what? Compression ratio of 20 to 1. All right, the compression ratio is 20 to 1. I'll remember that. Combustion releases 1,300 kilojoules per kilogram. Well, this is the combustion right here. See, there's no heat transfer on these adiabats, but there is here. There is a heat transfer of 1,300 kilojoules per kilogram, right? Yeah. Find the temperature after cutoff ratio. Well, we'll talk about that. Well, let's make our little table of values here and fill it in. That'll be fun. Okay. We need this room here. That's right, here we go. 1 to 2, 2 to 3, 3 to 4, 4 to 1. See that? That there is the Q 2, 3. It's 1,300 kilojoules per kilogram. All right, and we're going to have pressure, PVT, delta U, Q, and W. All right. Okay, now at state 1, we have 300K. And keep in mind that we're dealing with air. It's just it's going to be mixed a little bit with diesel fuel. But it's mostly air. The temperature is 300 and the pressure is 95 kilopascal. And this is 300K. Let's pause and get the specific volume. Now we're back to metric. P1V1 equals RT1. And we know R is 0.287 for air. So go ahead and find V1 for me. Go ahead. And I'll call on somebody here in a minute. What we're doing right now is we know T1, we know P1, we know R, and we're finding V1 using air. It's a diesel cycle. Cameron, do you have that specific volume yet? Cameron,
No, not yet.
he's working on it. Cameron's working on it. Take your time. Now there's also going to be a heat transfer out. We'll put that right here. That's Q41. That's the heat transfer out. What that is the exhaust. It's warming up Oklahoma. That's hot exhaust. So warming up Oklahoma. Well, I don't know. Cameron, are you still working on that, Cameron?
Yeah, I'm still working on it.
Take your time. How about my friend Bear? Bear, do you happen to know what this little V is right here, Bear? Earth calling Bear, come in, Bear.
Isn't that the specific volume?
Yeah. What's the number? What goes in that box, Bear?
Oh, just a second.
We're doing the ideal gas law, and we're looking at state 1. It's right here. And we need the specific volume. Bear, what'd you get? I bet my friend Cameron's got it by now. Cameron, what'd you get?
Just to be, I'm not sure. What's the R value?
0.287. Temperature is 300.
Is it 0.9063?
That's what I got. Now those are cubic meters per kilogram. Now they said the compression ratio is, read it, what does it say? 20 to 1. The compression ratio, what they're talking about is V1 divided by V2 is 20. See, this V1 right here is 20 times what the V2 is. So if you want V2, just divide by 20. Here goes, 0.9063 divided by 20. I'm getting 0.0453. I divided by 20. So we got that. Now, do you see that from 4 to 1 is let me go to Aubrey. Aubrey, they have a name for this process going from 4 to 1. What's the name of that process from 4 to 1, Aubrey?
Isochoric.
It's an isochoric process. You've got one isochore. And so, see, I know that V1 and V4 are the same. Look at here, 0.9063. Look at, we're making some progress. There we go. Well, let me read on here. Maybe I'm missing something. If you just woke up from a daydream, we're doing 1072. I don't think I've used all the info here. The compression releases 1,300 kilojoules per kilogram. Well, that goes right here. Not compression, the combustion. The combustion releases, that's this is the combustion from 2 to 3. And this here is 1,300. Oh, gee, I wonder who that is. Just a minute, I'm sorry. It's a white van out there, Karen.
Yeah, flowers.
So you're okay. Okay, now let's see, where were we? I got interrupted there. Oh, yeah, we got that 1,300. But see, that's kilojoules per kilogram. That's what that is, kilojoules per kilogram. Now, is there anything else I missed here? Let me read this. No, I think that's pretty much it. Okay. We got all that info. Now what? Well, how about you guys? You got any suggestions? We got a lot of empty boxes here. You know what? Some of these Q's and W's might be 0. Those are easy points to get. These are worth about 1 point apiece on an exam. Who was I talking to? I think it was Cameron I was talking to. No, maybe it was Aubrey. There. Let's go back to my friend Stuart. Stuart, help the class. There's some of these W's and Q's that are going to be 0, Stuart. Help us. Which ones are 0?
Is 1 to 2 and 3 to 4 0 for Q?
3 to 4 is 0 for Q. Good going, Stuart. Keep going, Stuart. I'm still listening.
1 to 2 as well.
1 to 2 is 0 for Q. Keep going, Stuart.
And is 2 to 3 and 4 to 1 0 for W?
4 to 1 is 0 for W because it's an isochore. But 2 to 3, there's work done there because you're moving. The piston's expanding. So that's not 0. But thank you for those 3. That helps. But these others, I think they have numbers that go in there. That was good. Okay. How about you guys? Do you have any suggestions? We've got a lot of empty spaces here. Anybody have any ideas? Got to fill all these in. They're a point each. Well, okay. Let me give you a hint. Going from 1 to 2 is an isentrope. It's a reversible adiabat. It's an isentropic process with an ideal gas. We're dealing with air. And you can use this equation that I developed for you guys, going from 1 to 2. Now, don't forget, these are 2 to 1, 2 to 1, but this is 1 over 2. It kind of flips. And the thing is, we know what T1 is, and we know everything here. We know everything here, so we can find T2. Here, let me write it for you. T2 over 300K is equal to, didn't they say V1 over V2 is 20? V1 over V2 is 20. Okay, I want you to solve that for T2. Go for it. And I'll go to one of my wonderful students here. Spencer, unmute and tell me what T2 is.
$4446.81.
So, Spencer, something bad happened. Either I goofed up or you goofed up. One of us did.
20 to the 0.9 times 300.
Well, 1.4 minus
4.
1 is 0.4.
Okay, it looked like a 9 on my screen for a sec.
Oh, no, that's my writing is at fault here.
No, I think it's my video quality, but it's 994.37.
Yeah, there you go. There you go. I need to make that my 4s more distinct. Let me write it bigger for you guys. It's 1.4 minus 1. So this turns out to be 994.3. Yeah, I have troubles with my 4s and my 9s. Okay, now, hey, look, P2V2 is equal to RT2. Look here, P2V2 is equal to RT2. I want you to find P2 for me. I'm going to do it. I want you to do it. And I'll pick on somebody else here. We'll ask somebody else here, but I want you to find P2 for me. Go for it. Aubrey, I've got P2. Have you got P2 yet, Aubrey?
I got 6,299.4.
That's what I got. We could round off, I guess. No, we'll just write it the way Aubrey said. 6299.4. That's what Aubrey said. 62. Yeah, that's good. We're doing great. It got hot, didn't it? It went from 90. No, wait a minute. That's pressure, isn't it? It went. Yeah, it got hot though. It went from 300 to 994. That got hot, all right. The pressure went way up. And now here's one of the dirty little secrets of the. What cycle are we doing? We're doing the diesel cycle. Do you see? This is the isobar. So 2 and 3 have the same pressure. 3 is 62, 99.4. So that's good. We know the pressure is the same. And I wonder if there's any other bright ideas there. Here's what we're going to do now. We're going to use this 1300 thing there. Let me make some room here, and we're going to see what we can do with that. Now, that's an isobaric process with an ideal gas, and I taught you guys that you can do this. I put a skull and crossbones over this, though. This only works with an isobaric process. Now, the truth is, it doesn't have to be an ideal gas either. I think I showed you that a while back. But see, if you have an ideal gas, then you can do this one here. But this equal sign here depends on you have an ideal gas. But we do, it's air with a little diesel in it, but it's basically air. And the thing is, we know what this is. It's 1300. It's given. See it? Isn't that nice? So we'll write it this way: 1300 kilojoules per kilogram. But see, in metric, this is 1004 kilojoules kilogram Kelvin. And what this will be is T3 minus T2. Hey, look, a nice equation with only one unknown. We can get T3 now. Now, if you run into a diesel cycle in your future sometime, this is really the dirty little secret of the diesel cycle, that this heat transfer is equal to the change in specific enthalpy. Isn't that nice? Okay, I'm going to shut up. I want you to find T3. Go for it. Hey, Stuart, do you have T3 for us?
I haven't finished working it out yet.
Take your time. It's going to be hot. Can you see that you're getting hotter? I really need to make that No, I think I made that pretty good. This 994, that's temperature at 2. At 3, it's the really hot one, isn't it? It's this one here. It's the really hot one at 3. How about it, Stuart? Do you have T3 for me yet?
I got 2,289.12.
That's what I got. 2,289. That's good enough. 2,289. Okay. Now, look here. P3V3 equals RT3. So what we're going to do is the ideal gas law again. Let's do it down here. P3V3 is equal to RT3. And we have T3. So we can get V3. We know P3 now. We know R, we know T3. We can get V3. Go for it. Go ahead and do that for me. And next on my list is my friend Spencer. Spencer, did you get T3 yet?
You just asked me if I found T3.
No, we know T3, Spencer. I'm sorry. What I meant was V3.
I'm still plugging it in. I just need to plug in my pressure real quick.
Yeah, go ahead.
I got 0.104.
Yeah, that's what I got. 0.1043. 0.1043. Hey, we're doing good. Now what? Well, I don't know. I wonder how you would. I got an idea. Going from 3 to 4 is an adiabat. It's a reversible adiabat. It's an isentrope. So here's what we're going to do. If I can erase all this. You know what we're going to do going from 3 to 4 with the isentrope. We have an equation for isentropes with an ideal gas. Now this equation only works if you have an isentropic process with an ideal gas. And I'm just going to go V3 over V4 because I know what that is. Well, no, I don't either. Yeah, I do too. Because I have V3 and I have V4, don't I? Yeah. Yeah, we can do this. Okay, well, what's T4? Well, we don't know. See, that's what we're trying to find out. T4 divide by 2289. And this is V3.1043.9063. 1.4 minus 1. Okay, solve it. Let's get T4. And can you read my writing? That's a 1.4 right there. It's not a 9, it's a 4. Okay, I did that. And I got 963.9. 963.9. Hey, we can get the pressure at state 4. You know how that works. Pressure at state 4. P4V4 equals RT4. And see, we know T4 now. We know R. We know the pressure. We can get V4. No. I got that wrong. We know V4. We can get the pressure at 4. Here we go. I'm going to do that now. I wonder if I did that right. Let me look and see what I got when I did it the other time. Yeah. I'm getting 305. Yeah, I think everything's right. Did anybody get 305?
That is what I got.
Yay. Now let me read this and make sure we're giving them what they want. This says, find the temperature after combustion. Well, this is the combustion right here. They call this combustion. That is, you're burning diesel fuel there. Now, what's interesting in the diesel cycle, you get a little bit of power during combustion. Do you see how the volume is increasing during the slow burn? Now, this is the power stroke, but you get some power in the diesel cycle during combustion also. So we're doing great. We've got a lot of stuff here now. Let's get these little delta U's. Now let me read this and see what they want here. They want cutoff ratio. I haven't told you what a cutoff ratio is, but well, let me tell you now. Now is as good a time as any. The diesel cycle has 2 ratios. They have the combustion ratio, and what that is V1 over V2. And they told us that was 20, I think. From memory, did they say 20? I think that's right. Let me make sure. I don't want to lie to you guys. Yeah, that's combustion ratio. Well, they have another ratio called the cutoff ratio. The cutoff. Diesel cycles have 2 ratios. That's V3 over V2. And I tell you what it is, it's 0.1043 over 0.0453. It's V3 over V2. Okay, well, let's get that. We'll see what the cutoff ratio is. I'm getting 2.3. So we got the cutoff ratio and the combustion ratio. But let's fill in the rest of our table. Here we go. Are there any comments or questions before we get those delta U's? Well, okay. Does anybody out there know how we're going to get these delta U's? Anybody out there know how we're going to get those delta U's?
CV delta T.
Yeah, that's one way, and I like it. And see, we can do it for each one. If you go from 1 to 2, then it's point, I think it's 0.717. Kilojoules per kilogram Kelvin times the change in temperature from 1 to 2. Oh no, I'm running out of space here. Kind of ran out of space there. All right, let's get that. Here goes. Well, I got the change in specific internal energy from 1 to 2 to be 497.8. Okay, now to go from 2 to 3, it's the same old boring thing. It's just you put in T3 minus T2. All right, let me do that. I hope you guys are following along. I'm getting 928.3. I hope you're following along. And to go from 3 to 4, it's the same old thing. Delta U from 3 to 4 would be the 0.717 times T4 minus T3. You're going to get a negative because it's cooling off. Okay, let's do that. I'm getting, I wonder if this is right. I'm getting a minus 950. These are kilojoules per kilogram. Let's see if that's what I got when I did this before. Yeah. Yeah, it's negative too. And finally, delta U from 4 to 1. Well, if you're going to go from 4 to 1, what you do is you take the C sub B, T1 minus T4. Okay, I can do that. Did you get a negative 476 If everybody's happy, we'll go on and finish this, but I'll stop if you have a comment or question. Okay, nobody said anything. Now on this one, this little W here, you guys know that delta U equals Q minus W. You know that. So this is going to either be a plus or a minus 497.8. Now whoever is going to answer this has a 50-50 chance of getting it right. Cameron, back to the casino, Cameron. Plus or minus on this 497.8, Cameron?
Would it be a plus?
Oh, Cameron, I've told you before, stay away from the casino. Stay away. It's a minus. Now how? Cameron, you can do this. It's minus going from 1 to 2 because of what, Cameron? Tell the class why the work per mass is negative going from 1 to 2. Why is it negative, Cameron?
I'm not sure. I'm thinking, but
He's thinking. Let me start to write it, and it'll pop into your head as I start to write this. Now you blurt in and you tell me the answer as I'm writing this.
compression.
That's it. That's it. Cameron, what about compression?
It's negative.
Yes, that's it. I don't have to finish, do I, Cameron? Compression work is negative. Expansion work is positive. See, a piston, here's a piston. If that piston goes up like this, you put a weight on there. See, it lifts that weight. That's positive work. Going from 1 to 2 is expansion. But our going from 1 to 2 is compression. Our 2 is down here someplace. And the environment is doing work on us. It's negative. The work is negative. Okay, now that was Cameron. I had fun with Cameron. Let me go to my friend Bear. Bear, this work per mass is either plus or minus. Oh, no, you can't. That's not so obvious, is it? Here, let me write it out, Bear. But going from, well, let me ask you this, Bear. I'll just ask you this. Going from 2 to 3, will the work be plus or minus? We don't know the amount yet. But Bear, what do you say? Will it be positive or negative work to get from 2 to 3? What do you think, Bear? 50-50 chance.
Shouldn't it be positive?
Yes. By Jove, I think he's catching on. It's positive. What is the reason why it's positive, Bear?
Because it's expanding.
You know what? There's hope for you guys. There is hope for you guys. You guys are going to be able to survive OSU after all. Are you going to OSU, Bear? Sometime?
Yes, sir.
Yeah. Well, I want you to do good, see? I've sent a lot of students to OSU, and I've seen a lot of students graduate from OSU and get good jobs. Hopefully this virus thing will be over and you can not have to do everything online someday. But now Bear knows that the work is going to be positive, but to get it, here we go. Here's what you're going to have to do. Going from 2 to 3. Now we have the Q, we know what it is. We have the delta U from 2 to 3. We can solve this equation for the work, and I'm going to do it now and see what I get. Here goes. Well, I got an answer. I came out with a positive 371.7. Let's see if those numbers work. If you take 928.3 and 1300 and you subtract 371.7. See, this minus is from your equation. There's no minus in there. That's a plus. That 371.7 is a plus. I think it works. That's good. Okay, let's go from 3 to 4 now. This is going to be a plus or minus 950. And we'll go to my friend, let's see here. Aubrey, we're going to do from 3 to 4. It's an isentrope. Is the work plus or minus, Aubrey?
It's positive.
Oh yeah, it's positive. There you go. We did great. And now we're going to go from 4 to 1. Well, there is no work from 4 to 1. Aubrey, how come there's no work from 4 to 1?
Because the area under the graph is 0.
That's a very good reason. There's no area under that straight line going down. You're right. That's a good enough answer. Another answer is it's an isochore. Oh, gee, we're almost out of time, but we got time to do this one. This is going to be plus or minus 476. We'll pick on Aubrey one more time. Aubrey, that heat transfer, can you see it's going out? It's the exhaust from 4 to 1. Is it a plus or minus 476, Aubrey?
It's negative.
Yeah, she knows it's negative. We did great. We answered all their questions. We have 2 minutes left. Wait a minute. Let's see if there's something else they wanted. And you don't have to do this. Well, you have to do it, but just turn it in the way we did it, because we did it for you. Find the temperature after combustion. Well, we did that. The temperature after combustion is 2289, pretty hot, Kelvin. Cutoff ratio, we did that. We found the cutoff ratio. It was, oh gee, we had it on the board a little while ago. It was, cutoff ratio was 2.3. We did that. We had 2.3. Now, we never did get to the mean effective pressure, but we could. I tell you what it is. It's the net work. Oh, we never did the net. Let's add these up. Oh, gee, we have a minute and a half. We can do this. Guys, when you add these up and you add these up, you don't get zeros. When you add these up, you're supposed to get zeros. I wonder if you do. Let me add these up and see what happens. I didn't get 0. I got 0.1. I guess I rounded off something wrong there, but basically it's 0. Now let me add these up. I think we had a little round off thing going on there. I'm getting 824 for the net heat transfer per mass. Now I'm going to add these up. Well, I'm getting 823.9. That's awfully close to 824. Again, I think maybe I have a round off error there, but we're okay. The sum of the Q's is equal to the sum of the W's in a cycle, and the sum of all the changes in any property is 0 for a cycle. If you wanted to do the mean effective pressure, you would take that 823.9, which is your net work, and you would divide by the change in specific volume from 1 to 2. Just take 2 minus, or 1 minus 2. There's the numbers, and you could get it. But it's we're out of time. Here's your last chance to ask me anything, because I'm gonna say goodbye here in just a second. Does anyone have anything to say? A parting word? So you got half of your homework done. Isn't that nice? Let's turn that in. But you're going to have to do 1074 on your own. Good luck. And most of you did okay on your exam. Make sure you turn your stuff in by the due date that's on Blackboard. Okay, that was your chance to say anything. Nobody did. I'm going to go bye-bye now. 5, 4, 3, 2, 1. Goodbye for now. See you.